I'm just going to give you all of us a quick overview. Spare me 10 minutes. I'll try as much as possible to finish within 10 minutes. Spare me fullest attention. We really need to get a big picture done. Then we go to the nitty gritty. Believe you me, that this is not a difficult chapter. Really not difficult. The calculation is easy, but I need all of us to understand the big picture. And I swear to you that if you can save this thing in your memory, actually, it's one of the most useful lectures you can ever have. So, let's start. First, I must say that we have learned about random variables. Am I right? Yes? We learned about random variables. Examples of random variables: score of a die, height of a randomly chosen student in VJC. Now, we have also learned that random variables, they are discrete random variable. Yes, and we have learned what are discrete random variables. Example: score on a die, and also the number of sixes obtained when tossing a fair die 5 times. Now this one, let's take a look at this. Number of sixes obtained when tossing a fair die. Why is it a discrete random variable? Because if this is x, x can be 0, 1, 2, 3, 4, 5. Remember? And this is an example of a discrete random variable. Specifically, an example of a discrete random variable is what we call a binomial distribution. Now, there are many types of discrete random variable. This is just an example, a specific example of a discrete random variable. And we'll learn a binomial distribution. So far so good. Then you have learned it in the previous stats chapter. So far so good. Now, then what is this next one? This next one is what we call a continuous random variable. Now, a discrete random variable is discrete because it can only take on specific values. Score of a die, again, score on a die if x can be 1, 2, 3, 4, 5, and 6. Done. Standard fixed number of outcomes. Whereas for a continuous random variable, a height of a randomly chosen student in VJC. Now this is a random variable, but it's a continuous random variable. Why? Because x in this case can be 1.7, 1, 2, 3, 4, 5, 7, 8, 9, 1, 7, 5, Theoretically speaking, it can take on infinitely many values, because theoretically speaking, it can be measured up to many degrees of accuracy. So far so good. So let's contrast the two. All of us can understand what are they different, why are they different. Alright, now to represent discrete random variable, what do we say? Or we say, okay, let's use the score of a die as an example. We actually can say, if let's say x is a score of a die, score on a die, and to represent this, we can actually have this and say, oh, okay, probably x equals to 1, 2, 3, 4, 5, and 6. I can say this is 1 over 6. At 1 point, 1 point, 1 point, 1 point. This represents the probability distribution of x. I don't think anybody will dispute. This is what we call the probability distribution. Now, my job here now is to ask ourselves, how do we represent the probability distribution of a continuous random variable, how would it look like here? Are we going to have probability x equals to x? And are we going to have, say, 1.5, 1.6, 1.7? And then how does it look like? Do we have points? Or what? We'll find out later, but that's what we want to do. So what's good? So now, let's take a look. How do we actually get here? This 1 over 6 and all these things. We actually do it like this. I don't know whether you recall. If you toss, suppose we toss a die 60 times. We do 60 times, we count the number of times you get a 1, number of times you get a 2, number of times you get a 3. Correct? This is what we call frequency. Okay, maybe you get sometimes you get a 12, sometimes you get a 8, sometimes you get a 8, sometimes you get a 10, sometimes you get a 12, something like that. Like that, like that, you get a 10, and then you get you add up to 60. Now, but you will only do it 60 times. Now, what if you do it 600 times? If you do it 600 times, probably you get this. Probably you don't get this, you get more, very close to 100. If you do it 6,000 times, you will get probably all of them quite close to 1,000. How do we get from here to here? We take 1,000, all the values here, frequency, divide by total frequency, such that we will get a 1,000 divided by 6,000, and then I get 1 over 6. Long-term average value, if I don't do it 600 times, I do it 6 million times, eventually I will get 1 million, 1 million, 1 million, 1 million, 1 million, 1 million each. Therefore, out of 6 million, I get 1 over 6. This is as frequency tend to. I think all of us can get this idea. Now let's then cross over to what we get. What happens if you have a continuous random variable? Now we start off the same. We start the same way. We think about it. Now this time, x is the height of the randomly chosen student. But instead of counting here, how many is 1.5? How many 1.6? How many 1.7? How many 1.8? We can't possibly do it because we cannot count one of these, and then all are one only. Cannot count anything else. Even if you do it 6 million times, you're not going to get to any unique value for this. So let's suppose we do it 100 times. 100. That means you pick 100 students. Total frequency is 100. Now, we're not going to, again, we cannot count, and then we cannot have how many is 1.7, etc. And for simplicity's sake, everybody not very tall or not very short, between 1.5 to 1.8. Oh, so we get, Eunice is 1.5. Okay. So let's, for simplicity, or then we will construct what we call a histogram. Maybe histogram, just for simplicity, we get 30 here. We get 40 here. And we get 30 here. So far, so good. Now, This one we call frequency. Now, is it possible that this is 30, this is 40? Now next, what? Can I don't like this is a bit too rough. Can I cut it a bit finer? I still will sample about 100. I still sample 100. Okay, this time I don't sample 100, I sample 1000. I sample a bit more, but this time I cut it a bit finer. 1.5 to 1.55, 1.6 to 1.65, 1.7 to 1.75. So I have more strips. So it's possible I have like that, like that, like that, like that, like that, like that. Maybe I will have a 120 here, 180 here, 200 here, 200 here, 180 here, 120 here. Now, for simplicity's sake, let us suppose we get such nice numbers. But you for simplicity's sake. Now, theoretically speaking, now this is the crucial part, this is the most important part, I'll wake up. Most important part here. Now, from here to here, what do we want? We want to represent something. Remember here, as frequency tends to infinity, it will tend towards a probability. That means if you sample enough times, it will actually represent the theoretical frequencies, in a way. The theoretical. So now we're going to do two things. First, I let frequency tend to infinity. I sample enough, infinitely enough. Second, I cut it, the width, tend to 0. Then, theoretically speaking, now we are able to then construct a smooth curve. The curve will be smooth. And the third thing I'm going to do is I will divide this total frequency. This is no longer a frequency. I will take frequency, I will divide by something such that the total area is 1. In this case, let us suppose this. Now area, if you really calculate the area, is, this width is 0.05, right? 1050. Correct? 50. Now, theoretically speaking, I can divide this, all these values, if I divide by 50, this area will be 1. So I'm going to do 3 things here. From here to here, I sample enough such that total frequency tends to infinity. I cut it finely into small widths. And I allow my total frequency, this one, is such that area equals to 1. Now this represents the probability density function of a continuous random variable. Definition of a probability density function is such that the total area must be equals to 1. So that sums up what is a continuous random variable. How do we present the probability of a continuous random variable? There's no way in the world you're going to present it with dots, because you're never going to get dots, because you are only going to get small values like this. So this is what we call a probability density function of a continuous random variable.